Alright guys, what I'd like to do now is go over two more problems from your electric potential worksheet from class. If you don't have the worksheet, then that's okay because I've included the questions here so that we can go over them. We'll go over these two, and hopefully you'll see that these kind of apply to some of the other topics we've done this year. So I'm trying to help you be able to connect these things together. Alright, so the first problem that we're going to look at is a beam of electrons. So we know it's an electron. We know the charge. We can find the mass of that if we need to. It's going to go between two parallel plates of length 10 centimeters. It gives us the velocity of the electron as it enters that field, and then it tells us actually what the field is. Now we know the field always goes from positive to negative, and then it tells us that the electric field is 60 newtons per coulomb. And then it asks us to find the transverse displacement, this y distance. How far is the electron deflected? Now obviously it's going to be deflected towards the positive against the electric field, like an electron always is. So why is it being deflected? Well, obviously it's because there's some type of force there, right? Now we know that one of our AP equations is that the electric field is equal to the force divided by the charge. So let's go ahead and plug that in. We know that the electric field, is 60. We're going to solve for the force, and then Q, our charge, is negative 1.6 times 10 to the negative 19th coulombs, right? And so now we can go ahead and solve for the force. So 60 times 1.6 e to the negative 19th. And we get 9.6 times 10 to the negative 18th. Just like that. Now that we know the force, okay, we know why it's being deflected. Now we're looking for a distance. Now how are forces related to a distance changing? Well, we know that distance will change if the speed is if there's something with the speed, right? And so speeds are then somehow related to the force because force equals mass times acceleration. So we're going to bring in Newton's second law here, that force equals mass times acceleration. Now the force being 9.6 times 10 to the negative 18th newtons, of course. And then the mass for an electron is 9.1 times 10 to the negative 31st kilograms, and then we can solve for the acceleration. So we'll take that former answer and divide by 9.1 e to the negative 31st, which is 1.05 times 10 to the 13. So acceleration equals 1.05 times 10 to the 13 meters per second, which is a huge acceleration, but it's a small particle, right? Okay, so now we've got our acceleration. That's acceleration in the y direction, right? Because it's got to be in the same direction as the force. The force is purely up towards the positive charges, and so therefore the acceleration is also up. Now at this point we've got an acceleration, we've got some other things, so let's go ahead and write out what we have. We know that this is going to be some type of now kinematics because we're looking at accelerations and distances. So let's go ahead and write out, we've got displacement, initial velocity, final velocity, acceleration, and time. Now in the x direction we've got a displacement of 0.10 meters, right, 10 centimeters. The initial velocity is 8 times 10 to the 6th. The final velocity is going to be the same because nothing's pushing it horizontally. The only forces are upwards towards the positives there. So no acceleration. And so we don't have the time, but it appears that we can get that if we need it. The horizontal displacement is actually, vertical displacement is what we're actually looking for. So now we'll look at the initial vertical velocity, which if it's coming in horizontally, there is no vertical velocity. The final vertical velocity, well, there is going to be a number there because now it's going up at an angle, so we have a component there. Now the acceleration, we have that, 1.05 times 10 to the 13th meters per second squared. And then we don't have the time. Now it looks like in order to get this y, we're going to need one other piece of information, which is probably going to be the time. So let's go ahead and use our equation that says x equals x naught plus v naught t plus 1/2 AT squared, and we'll use that with the x information to get the time. Now for the x information, the initial displacement, initial position will be 0, and then the acceleration, of course, will also be 0, leaving us with v naught t. And so if we take the position, which was 0.10, and we divide by the initial velocity, which was 8 times 10 to the 6th, then we get 1.25 times 10 to the negative 8th, which means that the time is going to be equal to 1.25 times 10 to the negative 8th seconds. Okay, so let's go ahead and put that in. 1.25 times 10 to the negative 8th, which will be the same time for this one. That tells us how long it's spending inside that inside the parallel plates. Okay, now assuming that the electric field is constant between there, then once it gets out, then it's going to be released from the field. Okay, now we can solve for y now. We're going to use the same equation, but the initial position is still going to be 0. This time we have a 0 initial velocity, but we do have 1/2 AT squared, so that will be 1.05 times 10 to the 13th times 1.25 times 10 to the negative 8th squared. So let's go ahead and plug that in and see what we get. So 0.5 times 1.05 e to the 13th times my answer from up there squared, and we get a distance of 8.2 times 10 to the negative 4th meters. So y equals 8.2 times 10 to the negative 4th meters. So that's going to be this guy right here, 8.2 e negative 4th. Very good. So now we've got part A, right? We've got the displacement of the beam. So now what it's asking for is, what is the angle? What direction is it traveling at now? Well, in order to figure that out, we need to know the two velocities, right? We already know the horizontal component. Now we just need to know the vertical component of velocity, which is this piece that we're missing here. So let's use one of our other kinematics equations. The simplest one is probably this one, v equals v naught plus at. And so the initial velocity for the y direction is 0. Acceleration for the y direction is still 1.05 times 10 to the 13th. And then the time is, of course, 1.25 times 10 to the negative 8th. And so let's go ahead and do that. And we get let's just do this. 1.05 e to the 13th times 1.25 e to the negative 8th. We get a velocity of 13,150. So 13,150. And then in order to get the angle, we just use Pythagorean theorem. We know that the x velocity is 8 e to the 6th. The y velocity is 13,1250. The angle then, right, is going to be the tangent of the angle will equal the opposite over the adjacent. So we want the inverse tangent of the answer, right, previous answer, divided by 8 times 10 to the 6th. And we get an angle of 0.94 degrees. So theta equals 0.94 degrees. And there we go. That's our answer. So I hope that that problem made sense. Obviously, it's a combination of a lot of different ideas. We used our electric field. We used the idea that that was going to give us a force. We used the force with the acceleration, with the mass to be able to get the acceleration. So we used a little bit of forces and Newton's laws there. Once we knew the acceleration, we were able to use that with kinematics over and over and over and over again to find out the displacement in the y direction and also the angle. All right, let's go ahead and look at one more because we got another couple of minutes here. This one is going to be dealing with something a little bit different. We're going to be looking at a couple of different charges. We have Q1, Q2, Q3. It gives us their positions and then their charges. Now the question for us is find the electric potential at point A due to the three charges. Now we know from our discussion in class that electric potential is equal to K times the sum of the Q's over the R's. Okay, so if we're looking at A, Q1 would be 2 centimeters away, so 0.02 meters. We know that Q2, that would be 1 squared plus 1 squared, so that would be the square root of 2 centimeters. And then Q3, so that would be 1 squared plus 1 squared, 1 squared plus 2 squared, right? So 1 squared plus 2 squared, so 1 plus 4 equals c squared, so that will be the square root of 5. Okay? If you got stuck, that's okay. Just pause it for a second, work those numbers out. Again, this is square root of 5 centimeters. So now we should then be able to get the voltage. So we'll say voltage equals K times, now Q1 is 4 times 10 to the negative 6. That's what the micro is, negative 6, divided by the distance, which is 0.02. All right, now that's a positive. Okay, and then we'll say plus, now Q2 is also positive, so that'll be 2 times 10 to the negative 6, divided by its distance, which was root 2 centimeters. Now the square root of 2 is 1.41, so we'll say 0.0141, and then again plus, now Q3 is negative, so we're going to put a negative 3e to the negative 6 there, and divide it by its distance, which is square root of 5. Square root of 5 I don't happen to know off the top of my head, so 2.24. So 0.02.24. And so then we'll just add all those together and see what voltage we get. So let's go ahead. K is, of course, 9 times 10 to the 9th. And then we've got 4e to the negative 6th over 0.02 plus 2e to the negative 6th over 0.0141 plus a negative 3 e to the negative 6th divided by 0.0224. And we get 1871238. So that's 1, 2, 3, 4, 5, 6. 1.87 times 10 to the 6th. Volts. Okay? And so there we go. That would be the answer to that one. All right, let's go on to part B. All right, part B says now a point charge Q of negative 5 nanocoulombs, so that would be times 10 to the negative 9th for nano, moves from a great distance to point A. What is the change in potential energy? Okay, well, how is voltage then related to energy? Well, we know that the energy average, sorry, that's the electric field, that's not the energy. The energy is equal to Q times the voltage. Now the nice thing is we've already found out what the potential is at point A. And so if we bring it from an infinite point way the heck out here and bring it all the way into A, at an infinite point the voltage would essentially be 0, right? The potential, since it's so far away, these would be very big numbers, and divide by big numbers will give you something very, very small, 0. So we can say that we know that out here my potential is going to be 0. So when I've brought it to point A, what's going to happen? Well, let's take the point charge of negative 5 times 10 to the negative 9th coulombs and multiply it by our voltage, which is 1.87 times 10 to the 6th. And we're going to get negative 5 e to the negative 9th. And we're going to get a negative 9.36 times 10 to the negative third. So the potential energy then would be negative 9.3 times 10 to the negative third, 9.36, right, times 10 to the negative third joules. All right, so very good. Now, question C says find the potential due to the same array of charges at point B and the work done by the electric field if Q equals negative 5 nanocoulombs from A to B. So what I'm going to do is I'm going to let you try that on your own. I think I'm just about out of time on this video. So hopefully you should be able to find the voltage for B in much the same way. I'll let you know right now that your answer should be negative 1.5 times 10 to the 5th volts. Okay, that should be your potential at point B. It's a lot closer to the negative there and much farther from your positive, the bigger positive, so that's why you're going to end up with a negative voltage. And then the work will be equal to the change in the potential energy, which in this case you'll again use that QV, so that's going to be equal to the change in potential energy, which again will be equal to QV, which hopefully you will get something along the lines of negative 0.010 joules. Go ahead, give it a try, and hopefully you get those answers following the same procedure that we did right here. Just remember to add up the potential due to each of the different charges, and that should give it to you. All right, thank you very much for watching. I hope this is helpful. Later.